Welcome back. In the last lecture, we saw that our mass action expression for different chemical reactions changes based on whether you have one reactant or two reactants in a chemical reaction. And we're going to explore a little bit more how this dynamic of having either one reactant or two reactants alters the overall time evolution of chemical systems. By the end of this video, you'll be able to identify the order of a reaction, use the integral form of the first order rate equation to determine the concentration of a product at a given time in a reaction, and to describe the concept of a half-life. So to begin, we first need to wrap our mind around the concept of reaction order. And this is a pretty easy concept to understand. Reaction order is simply the total number of reactants that a mass action expression has as variables. So if you consider the reaction A yields B, the mass action expression dA dt equals negative Ka, this only has one reactant, A, as a concentration in this mass action expression. And so this is a first order reaction. Contrast this with a second order reaction, such as A plus B yields C. In this mass action expression, you have both A and B in this expression. And so this is a second order reaction. There are two reactants that are included in the mass action expression. And for a third order reaction, well, actually a third order reaction really isn't a thing. But you'll often see reactions that have multiple reactants on one side, like A plus B plus C yields D. But what it's important to recognize is that this is not actually one reaction that's occurring, but this is actually a series of reactions that has just been summarized in shorthand as A plus B plus C yields D. So this might actually be like A plus B yields E, and then E plus C yields D, with the net effect of the reaction being A plus B plus C yields D. And the reason for this, why you don't have third order or higher reactions, is because chemical reactions are based on collisions between molecules. And for a second order reaction, you can definitely have two molecules that collide and cause a reaction. But the chance that three molecules are all going to collide at the exact same instant in the exact same spot is just so vanishingly small that in practice, you never see reactions that are of the third order. It's always just a multi-step reaction. A multi-step reaction that might occur so quickly that it appears to just be one single reaction. But if you drill down to the molecular level of what's happening, you're always just having two reactants or just one reactant produce a product. So this is a summary of reaction order. Let's move on and see how this affects the rate of change of chemical systems.
Okay, so let's begin by considering the first reaction that we considered last time, which was A yields B, a reaction with a single reactant. And we developed a rate expression for that. We said the change in the concentration of A with respect to time would equal some proportionality constant multiplied by a negative because A is decreasing as the reaction progresses. Some proportionality constant multiplied by the concentration of A. And this is nice. This is an instantaneous rate equation. So this, if you know the concentration of A at any given instant, you can say what the rate of reaction is for that instant. But what this can't tell us is what the concentration of A will be 30 seconds or 30 minutes or 30 days from now. And the reason is because this doesn't stay constant. As the reaction progresses and the concentration of A progresses, the reaction rate slows as well. So this is an instantaneous rate expression, as any differential equation with respect to time is. But it does not tell us, it does not give us a way to predict what concentrations are going to be in the future, at least not yet. But let's see if we can develop an expression that can get us there. So what we want is an expression that is the sum of all the instantaneous changes over time, which of course is an integral. So we just need to integrate this expression, and we should arrive at an expression that can relate the present state of the system to a future state at a finite time difference in the future. So we solve this differential equation just by separation of variables. Again, one of the oldest tricks in the book for solving differential equations. And what we can do is we can multiply through by dt, and divide by the concentration of A to get all the A variables on one side and all the T variables on the other side. So both variables are separated in the equation. Again, K is a constant, so we don't need to worry about K. And so if we do this, we can arrive at 1 over the concentration of A dA equals negative K dt. Okay, so now we can just integrate both sides of these equations. The variables are separated. Both of these are well-known integrals. The integral of 1 over A dA, as you might recall from calculus, is simply the log of A. And on the right-hand side, the integral of negative K dt, so put integrals here, is simply negative kt. Okay, so now let's evaluate these at 2 different time points to see how A changes as time changes. So let's pick a time in the future that we want to go to. We'll call it t, and we'll start at a time of 0. That's our initial condition. And we'll say that our concentration at time 0 is called A0, which we can say that we know. We'll say that given some concentration that we know now, what will the concentration be in the future? And we'll evaluate this to some unknown future concentration, A1. So if you evaluate both sides of this, this side is log A1 minus log A0 equals negative K T, we'll just call that T1, negative KT1, and then that's also 0, minus 0, so that doesn't really matter. By the property of logarithms, this is log A1, I guess I should have brackets around these technically, over A0 equals negative KT, T1, we're calling it. And then, so just exponentiate both sides, and you end up with your final concentration at time 1 over your initial concentration. Sorry, I keep moving these subscripts inside and outside of the brackets. Equals e to the negative k t1, your final time. Just multiply through by A0, and you end up with your concentration at time 1 is equal to your concentration at time 0 times e to negative k t1. So this is a nice, beautifully integrated equation that can tell you, given starting concentrations at one time, what your concentrations are going to be at a different time. So if I know what my initial concentration is, and I know the rate constant, I can just plug those values in. I can pick some arbitrary time in the future, which should be in the same units as k is in. So if k is in units of seconds, I can just plug in 300 for t1 and solve for this. Just, calculate this out, and this gives me my concentration at 300 seconds. So, very useful equation.
So again, here we have the integrated mass action expression. The concentration of A at time t is equal to the concentration of A at time 0 multiplied by E raised to the negative reaction constant times the amount of time that's elapsed since time 0. And you might recognize from this formula, or you can recognize from this graph over here, that this is your classic exponential decay formula. So A starts off high, and then it exponentially declines, and then asymptotically approaches its final concentration of 0. And a really nice feature of exponential functions like this is that although this is curvilinear when these time units on the x and y axis are linear time units, Say you took the log of the concentration of A. So instead of having A on the y-axis, you have log A, or we'll say log base 10A. If you take the log of A and put that on the y-axis over here, and time is still linear on the x-axis, you now see that you have a linear relationship between the concentration and time. And the slope of this linear relationship is simply negative k. And so this is a nice feature because what you can do is, say you're wondering, does a reaction that you're looking at obey first order kinetics empirically? You can just plot all your concentrations of log of the reactant on a graph like this, and if they form a line like this, you know that your reaction obeys first order kinetics, and you can also deduce your rate constant. It's simply the slope, the negative slope of this line is your rate constant. So that's an exploration of what the total time evolution of a first order reaction looks like. It's an exponential decay of the products, or of the reactants, and similarly you'd have an exponential increase that asymptotically levels off of the products. And if you transform both of these into log linear space, so log on the y-axis, linear on the x-axis, you end up with a straight line. Okay, but you might protest. Right now we've just been considering A yields B. But we said in the previous lecture that all reactions are reversible. So what about the reaction B yields A? Won't that impact our results? Well, the answer is maybe. Sometimes it will. But it all depends on the thermodynamic favorability of the forward reaction versus the reverse reaction. And I'd just like to make analogy to, well, not really analogy, this is a chemical reaction that's occurring, the combustion of wood to form ash. So this is theoretically a reversible reaction. Wood can form ash through fire, and ash can form wood through reverse combustion. That's an analogy to photosynthesis that occurs abiotically. But the thermodynamics of this reaction is so heavily favored in the forward direction. There's so much entropy increased by burning wood, and creating wood from ash and carbon dioxide would cause so much entropy to decrease that this reaction is strongly thermodynamically favored in the forward direction. So basically, you can say that the change in wood in the forward direction, that is by combustion to ash and carbon dioxide, is equal to the total change in wood of the reaction in both the forward and reverse directions, because the reaction proceeding this way is basically thermodynamically impossible. It's not theoretically impossible, but for all practical purposes, it is impossible because the thermodynamics favor this forward reaction so much. And so this is the case that you'll see in a lot of chemical reactions. In a lot of chemical reactions, the forward direction of the reaction is so favored that you don't even really need to take into account the reverse direction. This isn't always true, though. So you always need to be cognizant of your equilibrium constants when computing thermodynamics. And if your equilibrium constant has appreciable amounts of both products and reactants in it, then you will indeed need to consider the reaction going in both directions. But normally, I'll indicate this to you if that's something that you need to consider in a problem working in class. And generally, it will be apparent whether or not it is an important thing to consider. So again, in lots of reactions, you can just consider the forward reaction, but it is important to always have in the back of your mind that in some situations, the reverse reaction can be appreciable. Okay, now let's work a simple problem. A wastewater treatment plant has noted that the removal of nitrate in their flow-through bioreactors obeys first-order kinetics. So a flow-through bioreactor is where a reactant mixture flows into a bioreactor and it just flows through a channel very, very slowly. And when it comes out the end, a lot of the stuff that you're trying to react in that water has reacted by the time it comes out the end. So if water entering the bioreactor has a nitrate concentration of 450 milligrams per liter, and the mean flow-through time of the water in the bioreactor is 96 hours, so it takes 96 hours for a parcel of water to move through the channel and come out the other end of the bioreactor, what is the expected final nitrate concentration in the wastewater as it leaves the facility?
Okay, this is just straightforward application of the equation that we just derived. Concentration of NO3 minus at time 1 is going to equal the concentration of NO3 minus times 0 multiplied by E to the negative K time. And time here is time 0 minus time 1. So if we say time 0 is 0 hours and time 1 is 96 hours, the total flow-through time, then T should equal 96. So we just plug in our values. We have 450 times E to the negative 0.05 was our K constant, multiplied by 96 should be our final nitrate concentration at time 1. And you just plug this in your calculator, and this just works out to 3.70. And we're in units of milligrams per liter, so we can stay in milligrams per liter. The nice thing about kinetics is that you don't have to change back to molar units like you did for equilibria, unless your problem involves both equilibria and kinetics. So if you're just solving a pure kinetics problem, you can just keep the same units that you started with. So another useful thing that you can do with this is determine the half-life of a reaction. And the half-life is simply the time such that the concentration of, in our case, nitrate here, equals 1/2 the initial concentration. So this is the amount of time that it takes for the reaction to have consumed half of the reactants. And we can just rearrange this equation to get that. So if we know that we want this concentration to equal half of this concentration, we can just say NO3 minus times 0 divided by 2 equals NO3 minus E to the negative KT. Just divide through by NO3 minus on each side. You have 1/2 equals E to the negative KT, or natural log of 1/2 equals negative KT. And so just divide through by negative K here, and you end up with the natural log of 1/2 over negative K equals your time. And for this problem, the natural log of 1/2 is negative 0.693, and the K we had was 0.05, so negative 0.05. And I didn't figure this out in advance, so I'm just going to plug it into my calculator right now. And you end up with 13.9 hours. It takes 13.9 hours for the nitrate concentration in this bioreactor to be reduced by half.
So just to hit this concept again, the half-life of a first-order reaction is the time that it takes for the reaction to consume half of the reactant that's involved in the reaction. And you've probably heard of this in respect to like radioactive decay. Same principle applies, but this can just be a more generally extended analogy to any system that obeys first-order kinetics. And the formula for determining the half-life is simply the half-life equals the log of 1/2 divided by negative K. That's all I got for you. In the next video, we're going to explore what happens when you have reactions that don't just have one reactant, but have two reactants. So it's going to get thrilling. Stick with me.